So, hi everyone, my name is Judit Ferrer Asensio, and I'm a last year PhD student at the Center for Astrochemical Studies in the Max Planck Institute for Extraterrestrial Physics in Garching, Germany. And today I'm going to talk to you about this millimeter and sub-millimeter spectroscopy of doubly deuterated acetaldehyde. So in contrast with lots of the talks that we have seen so far in this conference, I am not going to talk about trying to find life directly, but I am going to talk about finding the constituents, so the building blocks for life, so these complex organic molecules. And I am going to focus also on molecules that are deuterated, so some of the hydrogens in the molecule are substituted by deuterium, which is really interesting to also follow, well, to understand the molecules formation and also their journey across the star formation process. So this is part of a paper that it's published. So if you are interested in accessing the full paper, you can do it so with this QR code on the bottom left of the slide. So let's go. So far, around 275 molecular species have been detected towards the interstellar medium. Although, as we have an average detection of 6 molecules per year, this number may have already increased. As you can see, we have this plot by McGuire 2021, where we can see the cumulative number of detected molecules over the years. These molecules have been detected on lots of sources that are in different stages of the star formation process. You can see here on the right this artistic impression of the star formation process, starting with diffuse clouds that contract to give pre-stellar cores. Then at some point these cores collapse, you form protostar, and then the material around the protostar starts rotating around it, and then this material flattens out into a disk. The dust in the disk coagulates, giving rise to planets, and then clearing out into a solar system. So some of these 275 molecules that we have observed towards the ISM, they are deuterated, and not even singly deuterated, but also doubly and triply deuterated molecules. And this is really interesting because the deuterium over hydrogen ratio on the ISM is of 2, more or less 2, 10 to the minus 5, which is pretty low, but we are observing lots, high abundances of these molecules. Deuteration happens mostly on the pre-stellar core stage due to the conditions we have in these clouds. Mostly the thing that is enhancing this deuterium fractionation, which is the substitution of these molecules with deuterium, is the low temperatures of pre-stellar cores. At these temperatures, the molecule that is the precursor for deuterium fractionation, H2D+, is favored. Moreover, at these temperatures, the main structure of H2D+, which is CO, is frozen into the last grains of the pre-stellar core, so then we have higher ratios of this molecule. So, as we said, well, here we have the deuterium over hydrogen value, and we're going to have this in mind to compare it to the observations that we see towards the interstellar medium. So this is a beautiful plot by Drozdovskaya et al. 2022, where we have the deuterium over hydrogen ratio on the y-axis, and on the x-axis, a big number of deuterated molecules observed. The different symbols correspond to different sources where these molecules were observed towards, and as you can see, most of these molecules oscillate in these yellow band, and you can see that this yellow band is way higher than the 2, 10 to the minus 5. So this is reflecting what we were saying about the deuterium fractionation. So in order to better understand the nature of this process of deuterium fractionation, as well as the interplay between the chemistry in the gas phase and in the surface of grains, we need to constrain chemical models with more observations of deuterated molecules. But to observe deuterated molecules, first we need accurate spectroscopic catalogs that are built from measurements in the laboratory. So in this project, we focus on this astrophysically relevant molecule, acetaldehyde. The main isotopolog was previously observed and towards the interstellar medium, and it was observed for the first time in the Sagittarius B2 cloud. And also the singly deuterated forms were observed towards this protostellar system, RS16, 29, 3, 24, 22, which you can see here on the right. And these detections were possible because we had accurate spectroscopic catalogs. On the other hand, for the doubly deuterated acetaldehyde, in the literature, we just had measurements between 8 and 40 gigahertz, which were not enough to build a catalog, and therefore there was no detection on the interstellar medium. Moreover, in the literature, we find different reaction pathways that try to explain the abundances of acetaldehyde, but these are still debated. If we are able to measure the doubly deuterated acetaldehyde and derive its abundance, we can maybe constrain these equations that would explain the formation of the main isotope block and also the singly and doubly deuterated ones. So acetaldehyde is a nearly prolate molecule which shows a internal rotation of the methyl group. So you can see here, we have here the carbon-carbon axis, and then this is the methyl group that can rotate. The numbers 3 and 2, well, 2 and 3, represent the deuterium atoms. So you can see that we have two main conformers for acetaldehyde, which is the symmetric and the asymmetric one, and this depends on the positions of the hydrogen and the deuteriums with respect to the plane that is built by this aldehyde group. So if the hydrogen is in the plane, we have the symmetric conformer, and if we have one of the two deuteriums in the plane, we have an asymmetric conformer. As you can see, we have two isoenergetic forms of the asymmetric acetaldehyde, and what happens is that these two configurations can tunnel amongst each other. What this tunneling does is to split the ground torsional level, and these can be seen in the spectra as closely spaced lines. So for the singly and the doubly deuterated acetaldehyde, we have three torsional sublevels, one coming from this symmetric conformer, which we call in, and two coming from the tunneling between these asymmetric conformers or out. This is in contrast with the main isotope block, which just shows two sublevels of tunneling between three equivalent configurations. And all of this to explain that it's difficult to fit the spectra of this molecule. But now that we have our the idea of the spectra, let's go to the lab. So in the lab, first we started by producing the sample. So we took main isotope block acetaldehyde and we mixed it with heavy water in an acidic medium at 38 degrees for approximately 2 weeks. When we had the sample, then we measured the spectra with frequency modulation absorptions experiment. You can see the experiment in this picture on the top right of the slide. This is here in the Center for Astrochemical Studies. And you can see a scheme of the setup here. So what we did first was to build a preliminary catalog with the previous measurements that were in the literature. And so with this preliminary catalog, we were able to record some lines at low frequencies, so low J's, and then upon recording more lines, we would update this catalog and continue measuring. So after months of measuring, we were able to record more than 700 new lines between this frequency range of 82.5 and 450 gigahertz. Here you just see some examples of the scans, and also you can see that the lines present this really characteristic second derivative shape, which is a consequence of this frequency modulation that I was telling you about, which is applied to reduce the noise of the lines. So on the first column, we have A-type transition, and on the second column, we have B-type transitions. As you can see, we measured way more A-type transitions than B-type transitions, just because for our molecule, they are more intense due to this dipole moment for the component A, which is bigger than the others. So now that we had all of these measurements, we needed to fit them to obtain accurate rotational constants. But of course, the problem is that the overall rotation of the molecule couples with the internal rotation of this methyl group, and this needs to be taken into account. So what we did was to use this approximation, this model, the internal axis model, which basically gives us rotational constants for the symmetric configuration, for the asymmetric configuration, and then it describes the tunneling motion between the asymmetric conformers. So what you're seeing here, these equations, is just the matrices that are describing this tunneling. So here you can see in this table all of the constants that we got. So here for the symmetric conformer, for the asymmetric conformer, and for this describing this tunneling motion. So this allowed to build an accurate spectroscopic catalog, which has a line uncertainty of 50 kilohertz in the 1 millimeter region. This is for A-type lines. So now that we have a catalog, the next step was to try to find this molecule in the interstellar medium. And we were really happy when we found it. So we detected for the first time this doubly deuterated acetaldehyde in the protostellar system, this Iris 16-293, 24, 22, where, if you remember, the singly deuterated molecules were observed. So we observed 48 transitions of this molecule in the ALMA-PILS data. And you can see an example here on the left, where the black corresponds to the spectra and the red corresponds to the model, showing some lines for our molecule. So from these observations, we were able to retrieve column density relations between the doubly deuterated and the singly deuterated acetaldehyde. And we found a percentage for a molecule of 20%. And this percentage is really similar to the percentage found for other icons in this same source, which can all oscillate around the 20%. So we have here methyl formate of 22%, dimethyl ether between 15 and 20, and methanol 20%. So this means that 1 out of 5 molecules, more or less, undergoes a second deuteration. And this points that maybe these molecules have a common origin, and this common origin should be a source where this really enhanced deuterium fractionation is allowed. And we think that maybe this is kind of showing at least a partial inheritance of these icons, these complex organic molecules, from the pre-stellar core stage to the protostellar. And this is really interesting. This is just the start of the work, because we have just seen these percentages now towards this source, but in the future, I'm going to be expanding these measurements to other molecules and other sources, and we are going to see, we're going to try to understand how deuterium fractionation works, and what are comps doing, where are they forming, and how long are they surviving in this journey of the star formation process, and maybe they are available for the formation of life. So in summary, we measured 700 new lines for the doubly deuterated acetaldehyde molecule. We produced an accurate spectroscopic catalog by performing a really specific fit of these lines, taking into account this internal rotation. We were able to detect this molecule for the first time towards the interstellar medium, towards this source, the protostellar system, the Iris 16-293. And we retrieve a doubly deuterated over singly deuterated ratio of 20%, which is really similar to other icons. And we think that maybe this could be a potential it could potentially tell us that molecules are partially inherited and there's not a total destruction of the molecules between this pre-stellar core stage and the protostellar core stage. But yeah, this is all for my part. I'm just saying keep your eyes peeled for the future, because I'm going to keep working on this and I'm really excited. So thank you.